here. All right, thank you so much for having me. It's an honor to be here. My name is Robert Hamnett. As Brother Matt mentioned, I'm an IT service administrator with the National Ecological Observatory Network, also known as the NEON project in the United States. I should mention that the US National Ecological Observatory Network is a project solely funded by the US National Science Foundation. Please note this disclaimer. So a little bit about myself. I've got about 15 years experience working in ecology and remote sensing in Hawaiian forest. I'm coming from the entire opposite side of the planet. I was born and raised in Hawaii, and much of my professional experience has just been out measuring trees. I worked many years with the US Forest Service and the University of Hawaii as a tree climber, plant survey and ID technician, and a tower technician, maintaining freestanding climate towers. Big ones, greater than 30 meters tall. So in 2019, as the NEON project was completing their construction on their final field site at Pu'umaka'ala Natural Area Reserve, not 10 miles from my house, I was lucky enough to join the team as a senior field ecologist in charge of the instrumentation on this shiny new tower with tons of sensors on it. In 2021, I joined the IT service desk, where much of my job is involved in facilitating observatory monitoring functions, including Grafana. I have a short video that would much better explain what NEON is, who we are, and what we do in 2 minutes than I could, and it'll also give you kind of a visual idea of what I'm going to be talking about. NEON scope is very broad, so I should mention before playing the video that if you want to learn more about the airborne platform or observational sampling, then just take a look at these links later.
From floods and wildfires to land use and invasive species, our ecosystems are constantly changing. The National Ecological Observatory Network, or NEON, is designed to collect data at field sites across the United States to help us better understand these ecosystems and how and why they change over time. The NEON project will transform scientists' ability to study our nation's ecosystems by providing a wealth of open data and a continental-scale infrastructure for research studies. NEON is unique in two ways. First, NEON uses a combination of data collection methods that are spatially integrated within and across field sites. And second, the data collection methods used are standardized across all sites to enable comparisons across the continent. As a result, the data can be used to integrate ecological observations across multiple scales, detect changes in how our ecosystems function, and enable forecasting of environmental change to inform resource management decisions. NEON field sites are strategically located in both terrestrial and freshwater aquatic ecosystems across the United States. They represent the vegetation, landforms, and climates of those regions. At each field site, NEON uses a combination of automated instruments, observational sampling, and airborne remote sensing technologies to collect data that characterize plants, animals, soils, nutrients, freshwater, and atmosphere. NEON's automated instruments collect data 24/7 at terrestrial and aquatic field sites across the nation. Flux towers that rise above the plant canopy at terrestrial sites collect a full profile of atmospheric measurements, along with sensors installed in the ground that monitor soil health. At aquatic sites, a smaller meteorological station collects atmospheric data, and other sensors monitor surface water and groundwater quality.
All right, so let's cut it
From
there.
floods and wildfires
Excuse
to
me.
land use and invasive species.
Next. Okay. Excuse me. So with that said, it is a great irony of NEON that the ecosystem that we're trying to measure seems like it's constantly trying to destroy our field sites. We've got animals nesting, pooping on, fighting with, and trying to eat sensors. We've got trees crushing sensors after windstorms. We've got lightning strikes. We've even got controlled burns around sites for fire mitigation. If you thought it was a challenge to maintain network infrastructure in a server room or scientific instruments in a lab, allow me to share with you an ode to the neon field science technician. So with that last video in mind, you can imagine how important it is to have a comprehensive monitoring platform. As Neon transitions to Grafana for site monitoring, let's compare our fundamental capabilities with the former state-of-the-art. So previously, on-site data visualization was extremely limited, and you could basically look at what was happening now, and that was it, with no historical look back. Monitoring and alerting was performed on batch data at 24-hour intervals. You can imagine how frustrating it might be coming from a field site only to realize something had broken just as you left, with the next site visit planned weeks in the future, sometimes days away, a drive that is. And then additionally, we didn't have any infrastructure monitoring. It was largely relegated to technicians logging into a switch to infer its status at any given point in time. Whereas with Grafana, techs utilize two instances. We have one that's on these servers at the field sites themselves that they can use independent of communications, and then we have an aggregated version in the cloud in GCP where you can look at near real-time data across the country from any field site. As well as having instantaneous alerts, we're using Victoria metrics, so we have those visualized over the time series. And then we also have now comprehensive monitoring capabilities across all of our infrastructure on site. So the transition to Grafana at Neon began in 2019-ish as we were replacing aging field site hardware. The back-end development started, but Grafana work didn't really start until 2021 when I joined the IT service desk. In November 2022, we deployed our first site at Central Plains Experimental Research Station in Colorado. And that was our first site to deploy this new software. We incrementally deployed it across the network and completed all tower sites in November of last year. There are generally 5 people working off and on this project, and my role is the field operations dashboard engineer. I maintain all the dashboards and design them that I'm sharing with you today. They're utilized by 77 full-time, talented, hardworking field technicians out in the field, as well as headquarters staff that help them coordinate maintenance activities. And with that, let's put on our imaginary work boots and hard hats, and let's take a tour of some of the dashboards. All right, so our target audience for the dashboards on site is largely the field science technician. They're not necessarily Grafana experts, so we try to develop a site-focused interface that includes a menu that divides up sites by sensor types and infrastructure into different dashboards, allowing technicians to drill down at different systems and subsystems on their site. When techs log into Grafana on their site, this would be the default landing page. Right now, we're looking at my former site, Pu'umaka'ala, or site code PUM, right at the top. Let's take a quick tour to get a sense of how we use these things. So at the top, we have some general stats that inform general site health, including power status and network status. Here we have a table that shows all the sensors streaming within a given site. Note the row count there. So at PUM, there's 116 individual sensors with multiple data streams. Here you can find out unique IDs for all the sensors, as well as their locations and other defining characteristics. This stat would show whether or not the site instance has synced up with the GCP instance. Since we have the ability to backfill the data when communications are down, we don't want technicians to infer missing data when it's just being backfilled. And if we were really on site at PUM right now, this wouldn't have any other options besides PUM at the top. But if we were looking at GCP, we could jump anywhere, to any site, and look at the same time series, which is really cool. Halfway down the page, we have some graphs showing our message volume for all the sensor data on site, as well as our interfaces and router traffic coming off the internet there. Moving down to the bottom section, the entire bottom half of the Site Hub is devoted to just general alerts for the site. The top features a stat showing how many alerts, where, and what kind of alert is firing there in the table. And then on the bottom, we have a donut graph that shows approximately the proportion where it's happening, and then temporally on a status timeline graph. Primarily, though, this dashboard is just the landing page to allow users to easily jump around their sites. I designed this menu before the Dashboard Select plugin had the ability to translate variables. So the idea is no matter what time series you're looking at or any variables you have selected, you should be able to click anywhere in your site, and they should translate from dashboard to dashboard, making it seamless. So getting onto the neon sensor data, this dashboard features all sensors that are defined as air sensors. When sensors are installed by technicians, they're given a set of context labels that inform what they are, what they do, and where they're located. In this example, I've jumped from Pu'umaka'ala in Hawaii to Kanza Prairie in Kansas. So if any technician ever has any doubt which sensor is in which dashboard, I list all the relevant dashboards at the top of the page, along with their preferred knowings and manufacturer IDs. Right below that is a cluster of panels that generalizes about just the alerts for all the sensors on that site, or excuse me, on that dashboard. This should help point techs directly to problems and not just overwhelm them with graphs. Here we see that a dual fan that typically aspirates an air temperature sensor is starting to fail for some reason. It's out of range. Maybe the flow might be restricted. What could cause something like that? Right. Neon towers have varying heights depending on the height of the surrounding tree canopy, and that translates to how many measurement levels and sensors that they have. So we can drill down to like a specific level on our tower by using our location variable at the top, and it filters all of our panels on for that location on the tower. So then let's select our time series for when this particular alert's firing and see if we can figure out what's going on. You might notice that this alert changes in severity over time. It's kind of slight, but it changes color there. We found that pending time intervals on alerts often missed intermittent failures, and so instead we applied a percentage over time, usually like 10% on the hour, before escalating the severity on an alert. When we scroll down to the panels featuring this alert, the sensor in this alert, I should say, the series is highlighted instantly red when it goes out of range. And we use this technique when it's just like a single data series that's out of range. So this is generally how techs would use a simple sensor dashboard, but let's look at something more complex. So all the sensor data that we collect goes into various data products, which we publish freely for the public. The most complicated data products from a tower site are the eddy covariance systems. These are some of Neon's flagship data products, which use sensors across the whole site, including wind sensors, gas analyzers, and they measure the movement of and storage of carbon dioxide, water vapor, and energy within a tree canopy. It effectively measures the breadth of an ecosystem over time. This storage exchange dashboard is one of 2 gas exchange systems that Neon sites feature. It is extremely challenging for a site to deliver a valid data product because of the number of sensors, infrastructure, automation, and scientific assumptions being made in the final data product. So monitoring all of it is essential. And there are many, many components. So let's dig into this dashboard. Again, we see alerts related to sensors in just this dashboard, but also we have annotations that tell us the status of the software that controls the automation for the air pumps and valves, et cetera. Additionally, we get an annotation if the exporter for the sensor data fails or if a data logger is suddenly not responding. This can help users infer when multiple issues seem to pop up across multiple sensors or data streams at once. We also have a relative link to Loki here, which provides links to the logs for the control software during the exact time series which you're looking at in Grafana, which is really helpful if you're trying to see if something is like real or a bug. So something like that. So before we scroll down this dashboard again, let's note this alert at the top that a rotary pump voltage is low, it's failed. So scrolling down, immediately we see in reference to this alert some stats, which are very red and very out of range compared to everything else in that series. This is a big deal. One air pump failing could invalidate all the data for the entire eddy covariance system. And depending on which one, these pumps aren't always available. And this is really what keeps tower technicians up at night, wondering when the next pump might fail. Here are some more stat panels, including reference gases, and several stat panels for the individual gas analyzers. Neon sites utilize automation to remotely calibrate and validate these gas sensors daily to ensure data quality, and it requires the use of compressed air cylinders on site. They're refreshed yearly, but they can be subject to leaks, and that can be really hard to detect and costly. Calibrations and validations also can't occur without this, and so the data is invalid and the data is lost. So this panel here shows the status of different valves on site used to sample air from different levels on the tower, as well as the valves that are used to control these validations and calibrations on site. To give you some idea of the complexity of the plumbing on a tower, I'll just flash this schematic. It's spaghetti. So this panel below here shows the concentration of carbon dioxide from the air measured across two different gas analyzers on site. And zooming up on these two panels gives you some idea of how we cycle sampling levels on the tower. Also what it looks like when one of the gas analyzers undergoes a daily calibration receiving low, medium, and high span gases. So this is a time series panel for all the air pumps on site, like what we just talked about, including the one that we just failed, that we saw just failed. It looks like it failed longer than 2 days ago, and this control software tried to run the pump again and failed, so someone's going to have to look at that. These are time series panels here showing all the different flows and pressures in the sampling lines. Comparing these values with pump voltages can help Neon technicians identify leaky plumbing or kink lines, which can break pumps, compromise data, and are extremely hard to detect. Here's where a suspected squirrel at Leno took a taste in Alabama. That's like halfway up the tower, by the way. Moving on, this panel on the top shows the water vapor concentration in the air from all the gas analyzers on site. These green spikes are actually generated by an auto-sampler robot that injects calibrated water samples into the lines and vaporizes them. While the bottom panel just shows the mass airflow controllers that can control how much flow, control how much air by volume is sampled. This is what the robot looks like. Moving down the page, the top panel here shows validation gas depletion over time. We actually have this corrected for fluctuations in temperature throughout the day in real time using an environmental probe and the ideal gas law. We're doing this with a query. It's pretty cool. It makes it a little bit easier to see when leaks are happening. The bottom panel there shows a 4-day delta that highlights if like one cylinder might be leaking more than the others over time. On the right here, we have pressure readings from all the gas analyzers with expected thresholds and set points visualized on the same graph. And finally, at the bottom of this dashboard, we have unadjusted gas loss on the left, which you can see is a bit wavy with temperature variations throughout the day, and the delivery pressure of all those cylinders on site from their regulators plumbed to the instruments. And the last panel here is the status of the many data loggers with an eddy covariance sensor related sensor plugged into it. And that's an eddy covariance sensor dashboard. It's a ton of panels and information, the point being that it all adds up to a data product. And even one of these panels indicating a problem could mean that the entire site's data product is invalid. There are other sensor dashboards with similarly grouped sensors with comparable data streams and shared infrastructure. We've looked at air sensors and eddy covariance dashboards, but let's look at some of the infrastructure dashboards. So as I mentioned previously, infrastructure monitoring at NEON was largely relegated to field technicians logging into a device like a switch or something and looking at the HTML interface and just getting a sense of how it's doing at that given point in time. The ability to look back historically at switch status provides a lot of information about the connectivity on each of those ports and what may have led to or caused a failure. Cable failures are actually one of the most common issues that NEON technicians face. So here we can see that a data logger plugged into port 3 has sent some bad traffic. Scrolling down, we see a state timeline graph, which shows an indication of all the data rate of all the sensors on that switch. We know that there is bad traffic on port 3. And we see the data rate across those sensors drop off for a second. Scrolling down, we see a time series graph showing when those bad packets were sent from the switch, and it actually seems to correlate temporally anyway, with the sensors dropping off above. But it's intermittent, so what could be causing that? This brings us to the last category of dashboards for site monitoring, which I've named Pilikia, which in Hawaiian means trouble. It sounded a lot more interesting than incidents, issues, and problems, which are pretty loaded terms. Anyway, so under Pilikia, we have dashboards that generalize about all the alerts on site, but we also have a dashboard completely devoted to diagnosing and detecting issues like this, like packet loss. So this dashboard, as I mentioned, is entirely devoted to detecting packet loss across the whole site and not just one switch. But it also includes some NEON sensor data that might help us infer cause. Here we see bad packets on our time series from soil plot 5 over the last week. We can see this behavior started on the 2nd, and there also appears to be a number of ports that sent bad traffic around the same time, around different points on the tower. Again, bad packets are usually an indication of like a physical problem with the connection or the port or the cable. Since one of the data products that we measure is rain precipitation, and we have rain sensors all over the site, and one of the most common failure modes is when a port or cable fails because of water getting into it, we can notice temporally that there's a correlation between this bad traffic and this rain event. And here, another rain event on the 3rd, we also saw an increase in the bad traffic from that same port. I can infer as a technician that this port likely has water issues, and there should be a data logger out there shorting or something, unless somebody goes out there and checks it out. Do you guys remember this picture from the sensor destruction montage? Being able to quickly test and visualize these metrics in real time and compare them allows us to do interesting things like translate these real-world events and scenarios into useful alerts, like there's water in your port, go check it out. And being able to compare NEON sensor data to infrastructure data helps NEON techs infer when the ecosystem that we're trying to measure might be responsible for the hardware failure at your site. Which brings us to the alerts dashboard, where we can find out information about all the alerts in the site within the time series in question. Again, we have general metrics related to alerts across the whole site, the addition of this time series graph counting average alerts over time. So with the same time series selected, we can see by filtering this table that we do in fact have an alert that says that there is likely water ingress in this port. Let's select that alert in this table and filter for just that. Selecting that alert filters it and gives us a link to the alerting component in Grafana, which allows technicians to find out more information about this alert. So let's find out more. So the alerting component has done a great job of rendering the alert rules from our alert manager and can show technicians exactly what we're testing and give them a summary of what we're trying to look at. And since we have all these dashboards replicated in the cloud, we can actually compare the number of alerts over time between sites. And that allows us to identify systemic issues across the observatory. I've also made dashboards to visualize those. I could go on for hours, but we're almost out of time. So as we near completion of the software deployment with only 10 sites out of 81 remaining, Grafana has already revolutionized the way that technicians maintain and monitor their sites, and we are excited to continue to find exciting and new ways to use this software. Thank you.